Okay, so obviously this unit circle I gave you is already filled in, but I'm going to talk about how how it gets to the point of being filled in and what it all means, because it is really useful. So if this is your last math class you're ever taking, um, if I'm being honest, you probably won't ever use the unit circle in your life, depending on what you study actually, but my guess is that you won't, or if you need it, you could go ahead and go on Google and look it up and you'll have it at your disposal. For this class, there are problems. All the problems that we do today will be based off the unit circle. If it was a standard semester, I would say you have to memorize or you have to learn what all of this is. And as soon as you get your exam, write it down on the back page. That way, when you get to a question where you need it, you have it there. That would be my advice. But where you're doing school online virtually, so with your exams, the way they're structured, just have this at your disposal. But I still think it's really important for you guys to understand what this all means and where it all comes from. So I'm still going to go through it as if you had to reproduce it on an exam yourself. With that being said, also, if you are taking calculus next semester or at some point next in your academic career, you are going to want to actually try to figure this out and try to know this because, like I said, it sneaks up on you. And I wish when I had first learned the unit circle that someone explained it to me this way. I didn't understand it, and it didn't stick in my brain until I took Calculus 3 sophomore year of college. And the first time I took calculus was a high school senior. So it took a while for me to actually understand what was going on. So I'm just going to explain what is going on. And hopefully that helps you in wherever you end up in your math career. Okay, so first, let's look at the degrees. Probably what we're most comfortable with, right? 0, 90, 180, 270, and this goes back to 360. Perfectly fine. Okay, and then we separate it into 30, 45, 60. You might remember from trigonometry, we had 30, 60, 90 special right triangles and 45, 45, 90 special right triangles. That's why we have these numbers. So we go 30, 45, 60, and then we go another 30 degrees to 90, and then add 30 degrees to 120, add 15 to 135. So essentially what we're doing is we're taking this first quadrant here, and we're mirroring it. So we still have this 30-degree angle that matches here, the 15-degree angle that matches this distance, 15-degree angle between those two, and then this 30-degree. And then we take this whole top part and we flip it over. And when we do that, we're essentially just either adding 30 if it's one of these bigger angles or 15 degrees, and that's how we get all of these degree measurements. Any questions there? Okay, now we're going to jump to the radians. I just ask that you keep an open mind through this. This can get confusing and messy. Keep an open mind. If you have an open mind, you will be able to understand it, or at least understand a piece of it and then ask me questions on where you're confused. Okay, radians. We have 0 to pi. That's our x-axis. It goes from 0 to pi. Okay, and then it goes from pi to 2 pi. 2 pi isn't written on this one. I could write it in if that helps you guys. 2 pi, but it's the same as spot as the 0. Okay, so if I want half of a pi, right? And anytime I say pi, you could literally think of it as a pi, but this time our pi is made in the shape of a calzone. Okay, so we have pi over 2. So this is just 1/2 pi, which makes sense because if we go from 0 all the way to pi, halfway between is 1/2 pi at the 90 degrees. Similarly, if we go from pi to 2 pi, that halfway mark is 3 pi over 2, 3 halves of the pi. Okay, right? 1/2, 1/2, 1/2, that's 3 halves of my pi. Any questions there? So now we understand the degrees of everything and the radians on the main axis. Okay, next it gets kind of exciting to me. All right. Still talking about radians, which is everything in this unit circle that has a pi. That's our radians, right? And we're talking just on the angle measurements. I'm not talking about any of this fluff on the outside. We'll get to that way later. So, I am going to, should be in this color, go ahead and pick specific angles to look at. Oops. So all of these that are highlighted in my teal. And we're just going to look at the top part. The bottom part is symmetrical. We do the same exact thing, and I'll talk about the bottom part after, but we're just going to talk about this top portion first, from 0 to pi. Okay, from 0 to pi, I have 6 of these teal lines. 1, 2, 3, 4, well, 7, but 6 angles created by this teal line. All right. Each of these angles is exactly 1/6 of pi. So that's why this first radian measurement is 1/6 pi. Remember, the radian measurement, when I say radian, it means that this arc distance here, where I'm tracing right now, that is the arc distance, the arc span is pi. It's 3.141, however, whatever units this is measured in, right? And this is the unit circle because the radius is 1. Okay? So now, this is 1/6 pi. If I jump and I tack on another 1/6 of pi right here, if I make my angle bigger and add another 1/6 of pi, I have 3 pi. But this could be rewritten as 2 pi over 6, right? 2 pi over 6 is the same as pi over 3 if you go ahead and simplify it. Then we have 2 pi, which that could be written as 3 pi over 6. Okay. Then we have the next 1/6 of an angle, or 1/6 of pi. The next angle is here it says 2/3 pi, or yeah, 2/3 pi, but I'm going to write it as 4/6 of pi. And then here we have 5/6 of pi, and then pi, I can rewrite as 6 pi over pi, 6 pi over 6. Okay. Do you guys agree that all these angles that I'm saying to rewrite mean the same thing? Do you agree, in other words, that 2/6 pi is the same as pi over 3 and 4/6 pi is the same as 2/3 pi? Do we agree with that? Good. All right. So essentially what's happening is where we have 1/6 of our pi, we keep 6 in the denominator and we increase the numerator by 1. So we start off with 1 pi, then we go to 2 pi, then 3 pi, then 4, 5, and here we're at 6 pi. Okay. We can continue this beyond pi. We could continue this into 2 pi, from pi to 2 pi. So we'll have here, this is 7 pi over 6. Here becomes 8 pi over 6. This, adding on this 6, becomes 9 pi over 6. Here we have 10 pi over 6. And here we have 11 pi over 6. Does that make sense? All right. So now we're done with dealing with the sixths. Next, let's go ahead and jump to the thirds. So I'm going to break from 0 to 2 pi, from 0 to pi up into thirds. And when I break it into thirds, I have a few green lines or a few teal lines that now turned purple. And that's perfectly fine. These purple ones, sorry, did that wrong. These purple ones each represent a third. Each of these angles is a third of the pi. Okay. So when we go from 0 to 1/3 pi, we literally have 1/3 of the distance from 0 to pi here. And that's why we write this in the simplest form of pi over 3. Next, we have 2/3 pi here. And then lastly, we have 3/3 pi. Okay, so it's all writing fractions just in different ways to kind of help us understand it and put it in the simplest form. So far, does the thirds of our pi make sense? Give me a thumbs up or something. Thank you. Okay. Next, if we continue with our thirds, we have this one, this one. We have that. 3/3 pi, when we add a third, we end up with 4/3 pi. And then we end up with 5/3 pi. And then once you get to 2 pi, I didn't mention this before, but this is the same as, 12 pi over 6 for our sixths, and 6 pi over 6 if we're talking in thirds. And that's not as important. Okay. Now we understand where all of the radian angle measurements that are circled, where they come from, and really it comes down to just counting, right? Once you draw your circle, make your little stars in between to get all your angles in there. It just comes down to counting. You're adding 1/6 or 1/3 each time you go around. Okay, lastly, we have the quarters. So our quarter angle measurements are anything that correspond to 45 degrees. So looking at the top half, the first quarter is pi over 4, 1/4 pi. The next one is pi over 2, but I could rewrite that as 2 pi over 4. And the next one is 3 pi over 4. And then lastly, we have 4 pi over 4. Okay, so again, we're just adding 1 in that numerator and keeping 4 in the denominator. And then you could go ahead and simplify your fractions if you want. Okay, from here, if we look at the bottom half of our, from pi to 2 pi, 1, 2, 3. Okay, from pi to 2 pi, I'm going to keep adding just 1/4 pi to my my previous fraction. So we have 4 pi over 4 becomes 5 pi over 4. This here becomes 6 pi over 4. And then we have 7 pi over 4. And then this would become 8 pi over 4, but like I said, that's not as important. Okay, so now do we understand where all of the radian measurements come from and what they actually mean? Okay, good. Next, we have to deal with the angles. And I'm going to time travel with you guys back to high school geometry for a split second. I enjoyed the class. I think I recall many people didn't, but maybe I was just different. It was also a cool class for me. My teacher did not like kids at all, but we were allowed to have a note card on every exam, so that was pretty cool. Okay. Back in high school geometry, you probably learned something called special right triangles. And I mentioned it earlier. Don't worry, don't freak out. You don't have to reproduce these. I just want to explain where our angle measurements, where the points on the circle come from. And it's based off of the special right triangle. So I'm going to start with the 30, 60, 90 triangle. And if you'll notice, that looks awfully similar to this triangle here, where this is 30 degrees, right? That means this is 60 and this is 90. Okay, so I just pull this out and we're going to take a peek at it. So I guess I should actually backtrack a little bit and just explain first what these values mean. All of these coordinates are, imagine if you took a circle, a perfect circle with a radius of 1, and stuck it on the center of it on the origin of any coordinate plane, any XY plane. Okay. These values here are where the circle intersects at that certain at the specific angle from the x-axis. Okay, so I wish I thought this out sooner because I would have brought up another picture, but just imagine a circle, this circle here, being placed on a coordinate grid, right? Like graph paper or anything with an x and y axis where the center is at the origin. Then this circle, these points tell us exactly where on that, if the radius is 1, exactly where on that graph the points for each angle end up intersecting the circle. Okay, so in order to figure out those points, we have special right triangles that help to pave the way. Here's the special right triangle. And in case you forgot, we have that the hypotenuse is 2x. This value here is x, and then this length here is x radical 3. In our case, can someone tell me what I said the radius is?
Would it just be 1?
Yes, yep, it's 1. So our radius is 1. So if our radius is 1, what is the length of the hypotenuse? It's not a trick question, guys.
I just have a question. So the radius would be that bottom, right?
So the radius is
If you could just like draw over it.
this distance here.
Okay.
Right? But it holds true for anywhere. All of these highlighted sections have radius 1.
So the hypotenuse would also be 1 then.
Correct. Yep.
Okay.
I'm just going to erase those, but let me know if you still need them. But yes, our hypotenuse here is 1. But 1 has to equal 2x, and this tells me that x equals 1/2. So that means if this side is 1, and this side is 1/2, then this side is radical 3/2. Okay. Anyone confused on that? I solved for x and plugged it in on the other two sides. Okay. Okay, remember I said you don't need to worry about your special right triangles. The same kind of concept works for the 45, 45, 90 triangles. I'm not going to draw that one out. I just want you to see at least for one angle where it comes from. But notice that I have some pretty sneaky numbers happening because I have, oops, not the color I wanted, radical 3/2 in 1/2 and radical 3/2 in 1/2. Right? Because remember, it's an XY coordinate. Even though it looks like it's on a circle, it's an XY coordinate. So we went to the right radical 3/2 and up 1/2. So the point here is radical 3/2, comma, 1/2. Similarly, the point for radical 4/4 is radical 2/2 and radical 2/2. The quarter angles were always my favorite. And I'll explain first with the quarter angles. If we follow the quarter angles, we have that the points are radical 2/2 and radical 2/2. The next quarter angle is, we're going to omit the axes. We're going to just skip over it because those are just the radius, right? 0, 1, -1, 0. But if we have, if we jump over to this angle, 3π/4, the coordinate point on the circle is negative radical 2/2 and radical 2/2. If we jump to the next one, we have negative rad 2/2, negative rad 2/2. And if we jump to the next one here, we have rad 2/2, negative rad 2/2. If we, for right now, just forget about the signs and just look at the numbers, every single point that is a quarter, that is a something π/4 on our unit circle, has the points radical 2/2 and radical 2/2 as its x and y, and the signs change. But if we're just looking at the absolute value. Okay, so one number that you need to remember in order to reproduce this, so you need to remember, right? I told you you only had to know 3 numbers. You only had to remember 3 numbers and where they belong, is rad 2/2. And you need to know where it belongs. After that, after you remember this number, you know that it goes here. You could put it here, here, and here. We'll worry about the signs after. The other 2 numbers that you need to remember are this point here. You need to remember the point rad 3/2 and 1/2. Honestly, I don't always remember which goes where. I don't always remember if the 1/2 or the rad 3/2 goes first. But I know that this length is longer, so the bigger number goes first, which rad 3/2 is bigger than 1/2. Plug it in your calculator if you don't believe me. Okay. Once we have that, whenever our radian has a 6 in the denominator, that is the number in the x and y spot. We have a 6 here. That is the number. Remember, we're not talking about signs yet. I'll get there in a minute. That'll be our final touches. Okay. Now all we would have left to do is fill in the π/3s, anything over 3. The 30, 60, 90 and 60, 30, 90 right? You only do 30, 60, 90, right? But the point is, if you were to flip the two, let me correct this yellow. If I were to draw this here, I'd have this is 60 and this is 30. So that means that my X and Y swap places. So you still only need to remember this coordinate, and then you need to flip the coordinate for everything that has a 3 in the denominator. Okay, does that make sense? Okay, the last thing that we have to do is fill in all of these signs, right? What's positive, what's negative? Okay. Maybe you could look at this and just say, here everything's positive, here only the X values are positive, here X and Y are positive, and here X is positive, Y is negative, because we're on an coordinate axis, and that's perfect. I'm going to take it a step further. And I'm going to give you, and this is, if you haven't been writing things down, that's fine. This you need to write down. I am going to give you the fact that we say X is equal to cosine of theta and Y is equal to sine of theta. And that's important to determine the signs, or to, well, I guess it might not feel important to determine the signs when we're looking at the unit circle on the coordinate axis, because we know what quadrants are, but it's important for how we use the unit circle. So all you have to remember is all students take calculus. Okay, might not be true, but just pretend it is and remember it. Because this tells us that in the first quadrant, all are positive. In quadrant 2, sine is positive. But remember, our sine is the Y values. So everything's negative, but sine is positive. Sine is positive. So only our Y values are positive. Here we have tangent is positive. I haven't mentioned that term at all, but tangent of theta is equal to sine of theta over cosine of theta. And if tangent is positive, that means that sine and cosine have to either both be positive or both negative. But we're only pointing out things that are positive in our little acronym. So that means sine and cosine are both negative. All right, so that's what tangent positive means. And then calculus means cosine is positive. Only our X values are positive. Okay. So that is how you put together the unit circle. The very important things that we need if you're just trying to get by and don't have a need or interest in learning about the unit circle and understanding it, I just ask you that you understand this here. And then we also have something called the Pythagorean identity. And the Pythagorean identity, I'm just going to erase a little bit of this to get it out of my way. The Pythagorean identity, is that sine squared plus cosine squared is equal to 1. So sine squared of theta plus cosine squared of theta is equal to 1. So this is also super important. And if you, just to further explain the Pythagorean identity, if you were to try to remember a squared plus b squared equals c squared, well, here on our unit circle, all of these hypotenuse are, or hypoteni, whatever, however you'd say it, they're all equal to 1. So that means that when we take this distance here, a squared plus b squared, we're going to get 1, which is why sine squared plus cosine squared is equal to 1. Any questions there? Okay. So I just went through all of this, and now we have a really fast worksheet to go through. So flipping to the worksheet. We have to find the exact value of these angles, the sine or cosine of these angles, without using a calculator. Luckily, we have a unit circle that answers these questions for us. So I'm going to do the first two led by me, and then the next 8 I want you guys to give me the answer for. So for problem A, sine of 5 pi over 4. So if I find 5 pi over 4 on this thing, let me do this first. Let me insert another one of these that's a little neater to look at. Okay, 5 pi over 4, so I have to look at my radian measurements. I'm looking for 5 pi over 4, it's here. I will circle it. Remember, x equal cosine theta, y equals sine theta. 5 pi over 4, and we're looking for the sine, so that's the y value, is negative 2, radical 2 over 2. So this answer is just negative rad 2 over 2. Okay. And then part B is cosine of 5 pi over 4. And 5 pi over 4 is in that third quadrant, so I know it's going to also be negative rad 2 over 2. Any questions there? For problem C, cosine of 2 pi over 3, can someone tell me what that value is on the unit circle?
Negative 1/2.
Negative 1/2. Good. Is anyone confused on where that came from? Okay, problem D.
Can you go over just that one?
Yep. So C, cosine of 2 pi over 3. So we go over to our unit circle. We find 2 pi over 3. I wish this would stop moving. 2 pi over 3 is here. The cosine is the x value, right? So it's
okay.
Cosine theta, sine theta is what points look like. And so we have negative 1/2. Problem D, sine of 2 pi over 3. Can someone different tell me what that value is equal to?
Radical 3 over 2.
Radical 3 over 2. Good. Next, we have problem E. We have sine of negative 90. What way does negative tell us to go?
Clockwise?
Clockwise. Good. So what is the sine of negative 90?
-1?
-1. Good. Any questions on that one?
Can you just go over how you got that, like using the circle?
Yep. So we went from 0 degrees to -90, which means we came down this way. And this point here is the point 0, -1. And we're looking for the sine of -90, which is the y value. So it's -1. Does that make sense?
Yeah, thank you.
Problem F, cosine of -2 pi.
Is it 1?
Does anyone have questions on that one?
When it's -2 pi. Oh, never mind. I see it.
Yeah, it just means that we started here and we went all the way around to 2 pi in the counterclockwise direction. But the coordinate that we ended up on is still 1, 0. So the cosine is still 1. Problem G, cosine of -pi over 6.
Radical 3 over 2?
Yep. Is anyone confused on that one or want me to explain that one? Okay, problem H, sine of -pi over 6.
Is it -1/2?
Yep. Any questions there? Okay, sine of 240 degrees, 240 degrees instead of radians, sorry.
-√3 over 2.
Yep, -√3 over 2. Any questions on that one? Okay, problem J, cosine of 240 degrees.
-1/2.
-1/2, good. Does anyone have questions on anything? If you don't have questions, you are free to go. Have a great weekend.